Yes, dedicated to the colleagues from Taiwan. Today we've got October the 12th in Germany, and we make a video conference prepared for November 11th. Would be a pleasure for me to be in Taiwan again, but according to the actual situation we have to do it like we do it now with the online conference. I hope it works well. Before I start my speech, I first want to say some greetings from our German associations. You know, it's ZWO and DGO, where I'm a member of the board or president. So best regards from our German associations, and as you see here, also from TEPNET, the electroplating association from Thailand. The colleagues from Thailand visited TSFA some time ago, learned a lot from you, so I also want to say the best regards from Thailand. Starting to that, structured chromium layer, I call it maybe a little bit a big word, change of paradigm in electroplating. Why a change of paradigm and why structured chromium layers? So I do not want to tell you now we had a big funny scientific idea and developed this and this out of that. I just want to tell you the true story, and the true story is that a customer of us, an electroplater from a normal job plating company, one day many years ago was standing in his production and thought, okay, here on this side of my production I've got rolls, and I do a lot of work in avoiding every kind what we call in electroplating burning on that rolls. In hard chromium plating, you know, burning means nothing else like rough layers, so we want to avoid that burning. We know that from hard chromium, we know that from nickel plating. And on the other side he had rolls where the application is printing machines, so rolls for printing machines, and these rolls have to be structured, had to be structured and still have to be structured today. And for these rolls he made a second production step, was a shot blasting production step, to make this structure rough. So he made this rough structure on the steel, then electroplated this with chromium to make a rough chromium structure on this side. And on the other side, he said he does a lot of work to avoid the burning and to avoid rough layers. So why has this to be so complicated? So we need shot blasting, electron discharge and everything to make structured layers, and on the other hand we avoid burning. Application, as I told you before, something like that. Rolls, they had diameter of something like 8 centimeters, 1.5 meters long for printing machine, and the real application is that some of these rolls just have to transport liquid in the printing machine, to transport the liquid to make the color, to give the color a specific viscosity. So his idea was, why can we not use, as Bill Gates I think was it, make the bug to a feature and to learn to control the burning, and this was where he contacted us. And then we sat together and thought about what does the normal hard chromium plater do when he ramps up his current density. At least in Europe he does this. I do not know if it's the same in Taiwan, but I think so. So the hard chromium plater, he always uses ramps. Hard chromium platers love ramps. And ramps in fact means they ramp up the current density. Of course they do not ramp up the current density, they ramp up the plating voltage in a kind of step function, so step by step up the voltage in different time steps until they reach the final current density, what we call the plating density. We thought about what is when we go to a higher level of the plating density, where we normally get into the burning, and maybe with this ramp we maybe can learn to control the burning in any way. So you know this, when we talk about normal hard chromium process, we've got 50 degrees of electrolyte temperature, then we go up to a current density of something like 40 or 50 amperes per square decimeter. And here in the first trials we went up to 80 or 100 amps per square decimeter. This is a very, very shortcut now. We talk about experiments that lasted for months or to be honest, years. And after all that, we learned when we play around in the step function with a higher current density and a lower electrolyte temperature, then we have a mechanism where we can in any way control the burning. So we can control the growing of rough structures. What you see here is all the same magnifications. I hope you can see it in the presentation. This is 100 micrometer of size, so we can say we can control the size of the grains we have, and we can control the number of the grains we have. What you see here, you look on the structure in the optical microscope, you look on the structure of a chromium plated layer, and what you see here, these dark dots, these are our structure elements. And obviously we can control the number and we can control the size of these grains that we build up. Of course, what you see here, these are extremes. This is nothing we can use for any kind of application. Maybe this one, but not this or this. This is what we learned, what we can control in our step function. And what you see here now, these are scanning electron microscope photographs from real application pictures. Here the size is a little bit missing, but you can say here the structure elements on this, the right-hand picture, is around 20 micrometers of diameter, and here it would be allowed maybe 40 microns of diameter. So these are real pictures from application. And what we found out then over the time is that we've got two areas of our ramp. So we've got, as I told you before, we can control it by ramping up the plating voltage step by step. We have another variation in the time we have between the steps, and we go up to a very high final current density. So we learned that we've got, in fact, three parameters we can deal with. This is the size of the steps in height and in depth, which means the voltage we ramp up and the time we have between the single steps and the current density we can go to. What I can tell you is that the time, so this is not something like a micropulse, the time we use between the steps is something between typically 2 and 10 seconds. So something what you can do with a normal electronic controlled rectifier. So we've got three parameters: delta U, delta T, and the final current density. And what we learned, and this is the interesting thing over the years, is that we've got two main areas of our ramp. In the lower area of our ramp, this is what we call the seeding area. In the seeding area, we can control the number of the grains we build up. Then we've got a transition area, we can control both of them a little bit. But generally spoken, on the higher area of our ramp, this is what we call the growing area. There we just can control the size of our bubbles we build. So this is what we see here. We can control the number and the size of the grains, the structure elements we build with two separate areas of our ramp, which makes it very interesting because we can play around in a very, very broad range of different structures. To underline this again, we do not control. This is a little bit, or this is the main difference to other structuring technologies in electroplating. We do not control the structure by any kind of chemistry. We use a real standard hard chromium electrolyte as you know it, so we do not use any fancy additional agents. We just control the structure by physical parameters in our ramp. The big advantage compared to using chemistry is when you put chemistry in your tank then you just have it in, so you've got no flexibility anymore. Here we have the maximum flexibility because we just have to use another rectifier program to get into another structure that we want to build up for different customers. So this is what we learned over a long time of experiments, which some or most of them have been done by production experiments, and then we went back. First we wanted to learn, can we really control something, and then we went back to the lab and learned how can we control it, and then when we saw we really can control everything, then we went back to the basic mechanisms. The basic mechanisms, this was the very first, or one of the very first pictures which brought us to the idea that there must be a very, let's say, different mechanism behind it than we use normally in electroplating was this. This is a cross-section through such a structure element. So what you see here, structure element, we just cut it here, and so we look into the side of this structure element. You see different things here. This is really a hemispheric structure element, so this is a base chromium we have here. This is our structure, and we cover the whole thing with a normal hard chromium layer anymore. We've got here a hard chromium layer, we've got a covering hard chromium layer, and this cross-section now is very strongly edged with the metallographic etching agents. Very strong edged, and what you see here, this structure surrounding the structure element, this is the normal structure that we would wait for when we etch a chromium layer. But in the center of our structure element, there's obviously something completely different from the point of electrocrystallization. We see a very, very fine structure here. Again, you see here the size 20 microns of diameter. So we thought, okay, something happens in here with the electrocrystallization. And when we think back, what we do in our ramp is that, I told you before, we use a relatively low electrolyte temperature and we go up to very, very high current densities. And obviously, when we do this step by step, then with a very sharp edge in there, something happens with a kind of change in electrocrystallization. And then we thought, okay, what can happen there? And then we went really, really, really far back. There's a very good book here, but it's a very old one, but extremely good, from a Mr. Fischer, and it's called Electrolytic Deposition and Electrocrystallization of Metals. And it's more than 700 pages where they deal specifically with the electrocrystallization of metals, very digging down in the mechanisms of that. And what Helmut Fischer found out, or gave the name, is four main different types of electrocrystallization systems. These are the shortcuts for the German names. It's called field-oriented isolated type, basic-oriented reproduction type, field-oriented texture type, and non-oriented dispersion type. To make it a little bit more simple, from the left to the right, you move, the higher you go or the farther you go away from the thermodynamic equivalent. Means from here to here, rise up the inhibition, rise up the current density, or lower the electrolyte temperature. This is what is in the definition of Helmut Fischer, and there's nothing better that was found out until now. So I think we can really say this is true. And what's also proven is that normal hard chromium layers, they do their electrocrystallization in this field, in the field-oriented texture type. This means of textures, pillars of crystals, they stand next to each other. And in the hard chromium plating, they grow in a what they say in a 1-1-1 structure. So all the crystallites they stand on the top of a cube. So when you think back now what we do in our ramp, we start here with the normal hard chromium layers, and then we go step by step with the current density. This means it is possible, theoretically here, that we change from here to this type. This means we change from the type where pillars are growing to a type where all our grains are completely unoriented anymore. And when you go back to this picture, then you maybe can get the impression that this could be right, that we've got the texture type here and the non-oriented type in here. Picture and theory, they match very well to each other. And now the secret was, how can we measure this? And then we went back to a very specific plating setup in our lab with a small beaker, 1.5 liter. And then we plated test samples. So these are CID drawings, these are the real pictures. This is the test specimen. It was completely shielded against the anodes so that we can have a real homogeneous electric field on these parts that we plated, because this was for real crystalline structure analysis made by our colleagues from Fraunhofer Institute for Mechanics of Materials in Freiburg. So we sent these specimens to them, and we made some specimens where we stayed on the hard chromium parameters, and we made some specimens where we went up in the very high level of our ramp, so where we plated in this way, and also sent this to them. And the analysis was, you see this here from Fraunhofer IWN. This is electronic backscattering diffraction analysis. So in fact they measure the texture of the crystalline structure from the hard chromium area. Only on this slide you could talk for 1 hour, but to make it short, this structure here, 111, is the typical structure in this analysis for a very, very strong 111 texture. So just what we were waiting for from a normal hard chromium layer. The interesting thing is now when we change over to the specimen made from our high ramp area where we build up our structure elements, then you see something completely else. In the same measurement, you see it here. This is the typical structure of a completely unoriented structure. So what we thought from theory from Helmut Fischer should happen in this thing coming from here to here, it really happens. So we change the crystalline structure on the chromium starting from the field-oriented system into the unoriented system, and this unoriented system is building up our hemispheric structure elements and is growing them specifically and separated, and then we cover the whole thing again with a normal hard chromium layer. So we go down again to the normal hard chromium specifications of our plating. Why do we do this? Quite simple. This one is much more soft than the normal hard chromium. So in here we talk about of a hardness from 600 Vicos or something like that. 600, 650, whereas in normal hard chromium plating we've got something, you know, that between 900 and 1050 Vicos. So we just cover the whole thing. Experiments have proved that we were right. So this is the model we have in there. When we are in the low part of our ramp, we plate with the normal hard chromium system, field-oriented structure, pillars are growing next to each other. And in that, we've got a statistical growth distribution, so it's always like one is a little bit, just when the grass is growing, one is always a little bit faster than the other. And then, in the same time, we rise and we rise and we rise the current density. And this means on one point, on the top of one of them who's faster, then we do the seeding, we change the crystalline structure. The crystalline structure to the unoriented texture type. And then it just happens that more or less only the new structure element is growing. Not completely only, but almost only. And this means that only our seeds then are growing anymore. And then we just, in the higher area of our ramp, we just let them grow. What we have seeded, we let them grow. This means in the higher area of our ramp we can control the size of our structure element, let it grow until they are as big as we want them, then stop the ramp, go back to the normal hard chromium plating parameters again, and cover the whole thing with the standard hard chromium. So this is a mechanism. I think it's more or less understandable. I hope it's more or less understandable that we can control with these different areas of our ramp and this understood mechanism, we can control the number of the seeds and we can control the size of our grains that we let grow. Second part of this speech now, I want to give you some short examples how this all is brought into production and different application, what is the advantage in there, and some specific things about the electroplating plants. Just to give you one example, we've got around 15 industrial applications in different fields of industry now. One relatively new application is, it's again a roll. Many of the parts we plate there are rolls. This is now a tool for plastic film production. For example, you need this when you produce displays. It's a deflector roll, and these plastic films, they have to be very, very smooth and shiny and everything. In this case, it's not that we need the texture or the structure to press the structure into the plastic film. The mechanism here is that this roll is spinning around very fast and we build up a kind of air cushion between this structure and the foil. So the foil does not really have contact to this roll anymore. And you see here, it's also a cooling effect, and what's very important there in this structure is to avoid any kind of wrinkles in this plastic film. And you see here again, this is the typical size of parts that are plated with this technology, dimension like that, and 1 meter and 80 centimeters long. This is a very relatively new application now. Another thing I want to show you, where it also goes into the end application. These are also rolls that are plated with this technology. What you see here, this picture on the right hand, this is an electroplating plant in a steel production company, POSCO in Korea, where they use this technology to plate these rolls. You see here, compared to this one, they're a little bit bigger. They've got a diameter of something like 50 centimeter and a length of 4.50 meters. And they are for cold rolling of steel sheet. And from this steel sheet later car bodies are produced. And they need a structured surface, because on the sheet, when you want to produce a car body, you need, for the formability of the car body, for example for fender or whatever, you need for the formability a microstructure in the steel sheet to hold the forming oil. This is the one thing. And the other thing is that the microstructure on the steel sheet, this is the decision-making point for the appearance of the painting afterwards. I will show you what it's about. So, in fact, you need a microstructure in the steel sheet. And traditionally, this is again made with a two-step production process, just how we began. Normally they do electronic beam discharge or laser discharge or something like that, and do the chrome plating afterwards for the wear resistance. The disadvantage there is that when you do electro discharge or laser discharge or something like that, you always have rough structure elements in here. The advantage we have here is that we've got those smooth hemispheric structure elements which are pressed as a negative in the steel sheet, and this gives many advantages, for example, when you go into the painting. In fact, what we do here, we do a chromium plating, but the product, in fact, is a steel sheet. And one of the advantages, one is the formability, but the other one is also the paintability. This is a slide from my colleague Michael Hilt. He's heading the painting department at our institute. And the big focus actually in the last year in the car painting is to get rid of one process step. Because when you think about painting a car body, means in the first step you go for the corrosion resistance in the electrocoating, cathodic electrocoating. Then you heat the whole thing up to 180 degrees, the whole car body. Then you go into the primer. The primer is there to make a very homogeneous and smooth surface before the color painting. You heat it all again up. Then you do the base coat, the color itself, do a flash heating, and then do the clear coat for the scratch resistance and heat the whole thing up again. And the dream now, in fact, this is the raw car body. So this is 400 or 500 or more kilos of aluminum or steel. And you heat this up completely 1, 2, 3 times, and 1 time flash heating up. And this means always a lot of waste of energy. The painting line in a car production is the most energy consumption thing in the whole car production. So the dream of them is to get rid of one production step. When you look in the production steps, then you cannot get rid of the electrocoat, because this is for the corrosion resistance. You cannot get rid of the base coat, because this gives the color that the customer wants. And you cannot get rid of the clear coat, because this gives the scratch resistance. But when you would have a very smooth and homogeneous steel sheet, then you can get rid of the primer, because the primer is only there to make a smooth and homogeneous layer underneath the base coat. And what is possible when you have steel sheet produced with these rolls, with this structure on it, and only with this one, is really that you can get rid of this primer section. And it's proven that this works because some, the very first ones now, but some painting lines in car productions, they are built up without any primer station. And this means not only that the painting line gets shorter and you do not need the primer chemistry, the main advantage is that you can avoid one time heating up this whole car body. So one thing. Second example in that is you see here products, a car and an airplane. And these products are known that they are made with a lot of carbon fiber reinforced plastic. The Porsche 918, the bodywork here is more or less complete carbon fiber reinforced plastic. In the A350, I think the bodywork of this one is made for 52% or something like that. More than 50% made of fiber reinforced plastic. So what does this have to do with chromium plating now? This is quite simple. For the same reasons I told you before, the smooth structure element that we have give again the same or another benefit here, but for the same reason. It's this soft structure element with the round shape, because when you go into the normal production for carbon fiber reinforced plastic, you've got a lot of contact points. In fact, the whole thing looks like textile machines. And when you've got polished surfaces there, then the contact area is too large. The fibers break. When you structure this with normal structuring technologies, with sharp edges in there, then you've cut the sharp edges and they cut the fiber. And the advantage is here again, this round-shaped structure elements on rolls or some eyelets like that. These are ceramic eyelets, not plated. When you use this in there, the customers tell us that the breaking of these fibers in the production goes down for 90%. And this gives you three advantages. The first one is, when you've got a lot of breaking of fibers like you see here, then of course you have to put some safety in the whole construction, because you do not know how many fibers get broken, and a broken fiber has no strength anymore. So you use a lot of the lightweight advantage of this material. This is the first one. The second one, when you look at the structure, this looks like asbestos. Yeah? And to have something like that, broken fibers, in the production, this is just dangerous for the lungs of the workers. And the third one is, these are rolls. So when these fibers break and they begin to spin around the rolls, then you have to stop the whole construction, the whole machine, cut these fibers off, and they are a horror to cut them. So you have to stop the machine, cut them off, with the risk that you damage something here on the roll. This is the third advantage. So the breaking of the fiber, to avoid the breaking of the fiber, is one of the main targets when you produce carbon fiber reinforced plastic. And this is the advantage in here, that with this surface technology we can bring down the breaking of the fiber significantly in production. So until now we were talking a lot about electrochemistry, electrocrystallization and everything, but the whole technology also has impact on the plating plant, the plating machine, because we need a very special plating machine. And the reason for this is the thing I want to talk about for you in the last minutes. As you know, we've got three different, what we call electric field distributions. We've got the first one, the primary one, which is pure geometry, what you see here. So this is the part to be plated, or this one. And when these are the anodes, then you know just from the primary electric field distribution, when we use plain anodes, we make an egg out of a round shape part. This is the primary field distribution, pure geometry. The secondary electric field distribution, this is everything what we call inhibition. We can do a lot concerning the inhibition of the electrolyte in copper plating and nickel plating. But all of you that are in hard chromium plating know that organic additives do not work in hard chromium electrolytes. We cannot use them in here. And generally spoken, when you've got a running system with fixed layer characteristics and everything, then you cannot work with that, because when you change the characteristic of the electrolyte concerning the secondary electric field distribution, then you also change the layer characteristics. So you can do this, but before you start plating. And the third one, the tertiary electric field distribution, This is everything concerning hydrodynamics, diffusion control. There we can not do anything else like make it as homogeneous as possible. And now when we talk about an in situ structuring technology, then of course we have to go into a very special precision, because when we say we plate rolls, we play something like a conveyor screw like that with a structured chromium layer and do the structuring from the plating process. This just means that we cannot do some grinding or anything afterwards, after the plating, because if we would do grinding, then we grind the structure away again, and this is what we do not want. And this means we have to go into a 100% net shape plating in here. This is the first reason why we need a very, very good primary electric field distribution in here. And the second reason is, I told you before, the ramp up of our current density. This is how we can play with the structure, we can control the structure in here. And of course, if we would have a bad electric field distribution on the part from here to the valley in here, a different electric field distribution, then this would mean that on this dot we would have another ramp than in here, and we would have different structures on the top and on the valley. And the customers do not want that. This means we've got two reasons: homogeneous structure, and we need to do net shape plating because we cannot grind the structure. We do not want to grind the structure away. This means we have to go into a 100% net shape chromium plating. And this of course has impact on the plating plants, especially everything concerning dimension stable anodes, very precise anode. This is the anode to plate this part. So this is not just any kind of standard plating anode. This is the rack and the anodes where we plate parts like that. So these are from ceramics, but they are also made of steel sometimes. And this is the plating setup for that. This is for other parts in carbon fiber reinforced plastic production. This means you cannot do this without a special plant technology. And this special plant technology we've developed parallel to electroplating technology itself has of course some other advantages. Because when we say we want to go into a net shape production, we cannot use any grinding afterwards. This brings us to a 100% material efficiency, because we do not grind any chromium away. We do not use energy for grinding. We do not produce waste from the grinding. This is a very, very material efficient process. And as in these plants, these are closed reactor plating plants, the complete rinsing water to avoid the loss of evaporation from the chromium electrolyte from the heat is brought back. The whole rinsing water is brought back into the plating tank again. This means every single gram of chromium salt we buy in the factories really goes on the part. We've got a really 100% material efficiency in here. And because we need such homogeneous condition in there, we developed also a very special plating setup, which we call a reactor technology. You see this here in practice. These are closed tanks. The whole factory, this is a hard chromium plating factory, and I think it really looks a little bit different as you normally know it. These are all closed reactor plating systems. We need this for the homogeneity, but they also bring us, of course, the big advantage that they are totally emission-free. This brings us to the last advantage in 2 slides anymore. Yeah? So this is how it looks in practice, how it looks in theory. We've got tanks where we've got the chromium and the rinsing water and everything, and in the reactors we've got the anodes, we've got inlet from the down of the reactor, on the head, on the top, we go back into the tank again. So we've got a separated thing. The chromium electrolyte itself and the plating department, which is closed, completely closed. You see this in here. There's a lid over there. This goes down, and in the plating condition, it's completely closed and emission-free. And this brings us to the last slide. You know, We deal with hexavalent chromium solutions, of course. These are dangerous substances, no discussion about that. And we have to take care that our environment and our workers are safe from this dangerous chemistry. And the process like that, because to use this electrocrystallization effects, we cannot use trivalent electrolytes, because you cannot go to this high current densities that we need here. When you remember back to the scheme of Fischer, you cannot do that with a trivalent electrolyte. This means for this we need the hexavalent chromium electrolytes. We've got the technology to make this safe for the environment and the worker. And this last slide also proves you that this is also okay for the legislation, because in Europe we've got the REACH legislation, which in fact shall ban any dangerous use of hexavalent chromium. And this is the original screenshot of Topochrome, who applied, this technology is called Topochrome, and also the factory is called Topochrome, who applied for an own REACH authorization. And you see here they have the use 12 years after what we call sunset date. This is a separate discussion. This is the longest term that you can reach under the REACH legislation actually. And this means that also for the European Commission, it's obvious that this technology is totally safe for the environment and for the worker. So, this was the last slide. I hope it was understandable for you. And I think we've got now 10 minutes for online video discussion. Please feel free to any kind of questions, and hope to see you again soon live in Taiwan. Thank you very much.